All right, we are on to partial sums of geometric sequences. And it kind of works similarly to what happened with arithmetic sequences. There is a formula, and our formula is given by S of n equals a sub 1 times 1 minus r to the n over 1 minus r. As long as your r is not equal to 1, because you know what happens when r equals 1 is that the denominator becomes 0. So if you're asked to find the sum or evaluate a series, what you might want to be on the lookout for is, double check. Do we have ourselves a geometric sequence? And so if you want to look at it, you can kind of say, well, let's look at this argument of the series. We have 2 times 5 to the k. And if we could look at that a little bit further, we might be able to, expand this out a little bit and see, is it geometric? That's kind of the first thing I might look at. So again, if I have this, I might say, well, what's the first term if I were to write this out? 2 times 5 to the first power. The second term would be 2 times 5 to the second power. Third term, 2 times 5 to the third. Let's write that 3 a little nicer. And there's more, but I just want to see what we have down. So 2 times 5 is 10. 2 times 5 square. What is that? 5 square is 25. 2 times 25 is 50. 2 times 5 to the third. 5 to the third, I think it's 125. 125 times 2. I'm using my calculator, by the way. I'm not a human calculator. So let's see, just by seeing the first 3 terms, do we have ourselves a geometric sequence? Okay, so let's say, how can we get from 10 to 50 by multiplying? I do know that 10 times 5 is 50. And then just ask yourself, is 50 times 5 250? And I use my calculator to verify it is. So that right away is giving me a heads up that my r is equal to 5. So what I've just done, just so that you kind of have an idea, is I just kind of expanded the first few terms to determine, first of all, do I have myself a geometric sequence? So I basically found what is a sub 1, what is a sub 2, what is a sub 3, and if needed, you could go and see what's a sub 4, a sub 5 if you can't quite see the pattern. By looking at this expansion, I already figured out who my first term is, which is 10. I also was able to determine that I do have a geometric sequence. Of the terms, I should say, since I was able to multiply the same number to get subsequent terms. So that tells me right away I have r equals 5. So if this is the case, we can go directly and use our formula. So we have S of n, partial sums. I'll write this down. A sub 1 times 1 minus r to the n, all over 1 minus r. And again, if we're looking at this partial sum, I'll have you notice right up here, you may not see it, but that is the sum of the first 9 terms. So what we'd be looking at is S sub 9. Now, if you know who a sub 1 is, which is 10, we have 1 minus, let's see, r is 5, so 5 to the nth power, again, over 1 minus r, so 1 minus 5. So you could take your time. We can go, actually, n, let me make sure. I'm supposed to be plugging this in. N equals 9, so we're even in better shape. We could directly plug all of this into our TI. I'll take a little time. I don't know what 5 to the 9th is, but I do know that 1 minus 5 is negative 4. So I'll go a little sideways for you. If I want to say 1 minus 5 to the 9th, I'll just go back to my TI. One minus 5 to the 9th, which gives me a large number. I could also plug these in as I go. Let's write that down. So I've got 10 times, it's a negative number, 1953124, all over negative 4. And then if it makes you happy, you could simplify again, or you could plug this all directly into the TI and see if you get a nice integer, which in this case we would, because we started off with adding integers. I do know that I have a positive answer, which we can go in and use our TI. I'll switch back really quick so that you see. And if I was plugging this in, I would have 10 times the previous answer, which was negative 1953124. So I have that, and if you divide that by negative 4, we would get our result. So what is that? Another million there, 4 million. So let's go back and record our answers. And I know there's other ways you can type all these directly in the TI. That's just the way I decided to do it today. So I have 4,882,810. So 4,882,810. That is considered the sum of the first 9 terms. You guys wanted to see kind of series notation. It's kind of a quick way to say this in English. So that's one way to do this. I kind of like knowing the formula and recognizing if something is a geometric sequence. Generally, this relates to, I believe it's Calc 2, where you start talking about whether series or sequences converge, and you use this formula quite a bit as long as you know it's a geometric sequence. So that's kind of neat to double check on that. For the purposes of this class, though, we do get to use our TI. And if we have ourselves a finite series, we could also just strictly plug this into the TI unless they're specifically asking you to demonstrate the use of the formula. So just kind of a note. Remember, it's looking at k equals 1 to 9. Argument is 2 times 5 to the k. What you can do is, let's go back. Go recycle some of our stuff from 8.1, previous part of the chapter. And you can use a few things. You can do sum of the sequence if you'd like, or we can use our notation in our calculator depending on what you have. So I'll do both ways just in case. I'll remember if we are doing this, we would press second stat. That's our new idea. We'd be looking at math to find sum. That's item number 5. We'd also be going back second stat to talk about the sequence. That's under operations. And then with our sequence expression, we should have ourselves, I have to remind myself, it's 2 multiplied by 5 taken to the x power. I'm just going to use that same variable. The starting value would be 1. The ending value in this case would be 9. And we're taking the sum of each term. So term 1, 2, 3, 4, and 5. So the step is 1. We'll highlight paste. And if you don't have that menu in your TI, you would be entering the syntax in as such, as you see. We can press enter and check that out. We got the same answer with a lot less work. It's nice in college algebra. However, the formula will come back to you eventually. So might as well kind of play around with it a little bit. Also, if you were interested, if you had your notation in your calculator already, you can go straight to math, and we could actually go to summation notation. That's item number 0. And however you'd like to use, x is going from 1 to 9. We enter in our argument 2 times 5 to the x. Press enter. And again, we get our same answer. So like I said, if there's nothing asking you to prove anything and they just strictly want what the answer is, that is quite okay if you want to use your TI. Sometimes it often helps with a lot of the minor errors that might happen as we go through the math on this. So remember, this only works for finite sequences. We're going to talk a little bit about infinite sequences in the next example, and I'll see you then.